for inviting me.
Of course.
I'm happy to be here. And yes, I will talk about segmentation. And first I thought maybe I should say a few words about Fraunhofer MEVIS, because we have probably never done that, Klaus. I haven't prepared that, but I will just quickly go on our website so you get an impression. So Fraunhofer MEVIS is the Fraunhofer Institute for Digital Medicine. So Fraunhofer is a society of research institutes in Germany, and it has, I think, 76 institutes with a wide range of different topics. So they are in different places, they do different things. They are also kind of independent, but they all belong to this Fraunhofer society. And the focus of all these Fraunhofer institutes is applied research. So we collaborate a lot with industry. We are also supposed to get about 1/3 of our budget from industry. So for either research that they want us to do, and also licensing. So we develop things and we license them to industry. That's part of what we do. And I think the first image here showed you, this is all our group, so it's more than 100 people, I think 100 researchers plus administration and other IT and other people that we need. And we're also in different places in Germany, but most of us are in Bremen, and that's also where Klaus and I come from. And if you're interested, you can go to this website and you can, for example, go to Research and Technologies and check out the different fields that we're doing. So for example, imaging physics, this is what Klaus is doing, for example. I'm more from the image and data analysis group. And then we have other things like registration, modeling and simulation, visualization, and also software development. So most of the people who work at Fraunhofer MEVIS are computer scientists, mathematicians, physicists. We also have a few people who have a medical background, but that's really, usually we do projects together with hospitals, and then we get the clinical expertise from there, and also the data. We are just doing research, we're not treating patients, we're not acquiring our own data, only for research purposes when we develop new MRI sequences, for example, but no really clinical work. Okay, then I'm going to switch back to the presentation. So maybe a few words also about myself. I'm a computer scientist. I joined Fraunhofer MEVIS in 2006, so it has been quite a while already. And my focus is, as I said, image analysis, mostly segmentation, what I'm talking about today. I studied computer science and I did my PhD here at Fraunhofer MEVIS. So you can do a PhD there, though it's not directly connected to university, but the director of the institute is also a professor at the university. So that's how you can do a PhD as well. Okay. And then I wanted to ask, before we start, you had some instructions to prepare software. Did you all manage to do that? That's great. Then we can also have some interactive sessions. I think that will be very helpful. I will also, when we do that, walk around and help you and check if everything works. Okay, so this is the plan for the session. So first I will talk about what segmentation is. Then I will talk a little bit about quality criteria for segmentation algorithms. And then two major parts, how did we do lesion segmentation? And I will always talk about tumor lesions, not MS lesions, because that's what I have been doing all the time. But I think it's similar enough to MS lesions so that you can learn something from it. I actually started working on that around 2010 when I joined Fraunhofer MEVIS, and I'm still working on it today. And as you may know, the way we are doing that and the methods that we have radically changed in the meantime, and I want to show you both, well, some aspects from both times. So what did we do like 25 years ago, and what are we doing now, and how is it different? So as I said, I will talk about tumor lesions in CT images. So on the two left images, you can see the mouse also in the presentation? I think you should. So you can see, for example, I hope that you can recognize it. There are some very small you see it? There should be some very small dots in the lungs here, for example, and here. If you can't see it, it's not important. You will see more images later. These are lung lesions, so metastases in the lung of some primary tumor that we don't know. Here you can see a liver with, at least you should be able to see this big one here. So metastases in the liver, and then for comparison, an MRI scan with MS lesions that you probably recognize better than I do. I just found this image in a public data set. So you can see that in both cases you have structures that look slightly different than the normal tissue. They have different intensities and they are often like round. I know that MS lesions are not always round, but at least some of them are. And these metastases that we often see in the lungs or in the liver, they are typically round and spherical. And that's also something that the segmentation algorithm will use. So I will talk about these examples from tumor lesions, but I hope that you will have the feeling that you can also do something similar for MS lesions, if you would like to segment them. Okay, so what is segmentation? Segmentation means you want to partition an image into semantically meaningful subregions, and in the case of medical images, these subregions are usually anatomical structures, so something like organs, tissue types. So you could want to segment, for example, muscle tissue, all kinds of organs, and also lesions or other pathological structures. You want to divide your image into these different regions. And you can represent that from a technical perspective in different ways. And the most common one is a label image, where you do voxel-wise classification. So each voxel of an image gets a label. For example, it's lung, in this case here, this is a lung example, left lung or right lung. And you can have different labels and background. And often you just have one structure that you're interested in and the background. And then you also say things like, I want to segment the lungs, which doesn't really make sense because you would segment the image into different segments, but that's what people say. So don't be confused by that. Then sometimes you also have something like a probability map. You can probably see that we don't have just 0 and 1 here, we have all the values in between as well. And that could mean something like the algorithm wasn't really sure, or also maybe the information in the image is not that accurate, so you can't be totally sure where the boundary of an organ is. And you can represent that by kind of a probability value between 0 and 1. You would sometimes see that as the output of segmentation algorithms, especially deep learning-based algorithms, because their output is something like this, and then you have to pre-process it. The third thing that you will often see is contours, and that's especially the case when you have manual segmentation. So if you ask your experts, or maybe you are the experts, you draw segmentations for us to train a segmentation algorithm on, then you will draw contours, and they are then converted into something like that, so they are voxelized. Because these contours can actually have a resolution that's higher than the voxel resolution of the image, because you just draw somewhere on the screen, right? And then I wanted to talk about automation. So when we talk about segmentation algorithms, many people think, oh, this has to be fully automatic, otherwise it's not helpful, or it's not worth a publication or whatever. That's not the case, I think. Because in many cases, it's totally fine to, for example, click into a lesion that you want to segment. I will get back to that. What kind of automation you need depends totally on the use case. If you want to have the volume of a lesion, for example, and you click in it, it's fine. If you want to process a whole image of, for example, compare sizes of different organs or whatever, then it has to be more automatic. And by the way, if you have any questions, just ask. You can just interrupt me anytime. But I will also ask you some questions later. What is algorithmic segmentation used for? I think there are two main goals that you can have. One is to improve the workflow in a case where you already do segmentation in the clinical workflow. So for example, in radiotherapy planning, you need to do it. And then of course it's helpful if it's automated or partially automated. And the other thing is to increase the accuracy of a measurement, for example. For these tumor lesions, the usual measurement is the diameter, because that's what you can do manually with a reasonable amount of time. But with segmentation, we could get the volume of the lesion, and that would, of course, be more information and more accurate than just the diameter. And often these two goals are, well, you don't really think about what your goal really is, and I think it's important to realize what of these two goals you have. Most of the time they are actually contradictory, because if you want to have more information, it takes more time, and then your workflow is not efficient anymore. So that's, for example, something that we tried to do when we first started with this lesion segmentation. Our goal was to provide more accurate measurements, but we realized that it takes more time. Even if you have an algorithm, you have to check whether the segmentation is correct, and maybe you have to edit it a little bit, and that takes longer than just drawing the diameter yourself. And we noticed that the radiologists didn't want to do it. So in that sense, we developed something that had a goal that was not accepted by the clinicians. And then at some point we said, okay, this doesn't make sense. Let's try to really improve the workflow, because that's where the actual problem in radiology is. It's typically not in accuracy, but rather they have too much work, and it's helpful for them to just automate something that they have to do anyway. So some examples what you can use segmentation for. One example would be volume measurements or other feature extraction. So you want to extract information that describes an organ or a lesion from an image. You need segmentation for that. Sometimes you do segmentation as a pre-processing step. For example, if you want to detect lesions automatically, you would first want to segment the organ where you are looking for the lesions, because otherwise you have to process the whole image, and it doesn't make sense. So you often do it as a pre-processing step. That's then more a technical application for some other application that has a clinical value. Then, as I already said, radiotherapy planning, that's where you really need segmentations, because you want to plan where the radiation should go. Other things are planning and navigation of surgeries or interventions, also modeling and simulation. I don't know that much about it, how you use segmentation there, but I know that it's needed there. And now maybe you have other applications that you know about, or that you can think about where you need segmentation. Do you have any ideas?
I mean, we use it to understand, let's say, a particular MRI biomarker within the tumor lesion. So we need to have the tumor segmentation at hand to be able to calculate further parameters. So I'm looking at which one that will be in this.
I think the first one with the
extraction of other measurements or features. That will be our main purpose of segmentation, actually.
And I think David will talk about brain atrophy tomorrow. You will need a brain segmentation, because you need the brain volume, right? Yeah. So that would be another, and that is something that is how is it done now? If you don't have a segmentation algorithm, do you actually do it by hand?
No, we don't do that anymore. But I mean, that's the starting point. I would say. That it would take several days to segment only one brain. And even if you want to do regional, it would take several weeks, I would say.
Okay. Yeah, that's a good transition, because one slide before that. But you will segment lesions manually in a few minutes, and then you will also see how hard it is, and you will be happy that we are developing algorithms for that. But before I do that, some technical things about medical images. Maybe you know this already, or probably, but just to be sure, we have 3D images which can be represented as a matrix, so just as an array of numbers, like in this example here. So for us, when we do image processing, an image is just numbers. We don't really care about how it looks. And also, you probably know that you can change the mapping of the gray values to these actual numbers that are the image information. So that's probably not new. We have a natural slice orientation that we can easily change. That's probably also clear. So we do that sometimes, that we format from axial to sagittal if that's helpful for something. But actually, for us, it doesn't matter because it's, as I said, it's just a 3D matrix of image values. Yeah, in CT, bright or a higher value means a higher X-ray absorption. So that's pretty clear what brightness means in CT. And also, by the way, for CT, these values are calibrated. They are Hounsfield units, and they have a physical meaning, unlike MRI. And when we do image processing, these values can totally change, and they have a different meaning then. So we just, again, it's just numbers for us, and we do things with it, and then we get different values that can have any meaning. And also the voxels have a known physical size. That's important if you want to make measurements and measure volume, for example, you need to know the size of a voxel, and that's known. So we can, in the easiest case, if you want to compute the volume from a segmentation, you just count the voxels and multiply it with the voxel volume. It's not the best way to do it, but the easiest. And you often don't have the same voxel size in all dimensions. So in the Z dimension, you often have a higher voxel size or a lower resolution. I think especially in MRI and CT, it's almost isotropic. We call that isotropic if it's the same resolution, and your voxel is basically a cube and not just a, how do you call it? I don't know, but it's something that we can also change and do sometimes. So we just recompute the image, we resample it to have that isotropic voxel size, because that's helpful for many things. Okay, now you can try that yourself. Who of you has already done manual segmentation? So who has contoured? Oh, most of you, or maybe half. Maybe it's not so exciting then, but it's a good introduction to the software that we will be using. So you can open that now, and you should have different MLab files, and there's one that starts with one manual segmentation.mlab. Yes?
I have a question about the previous slide where you explained resampling. I'm familiar with the concept. I have a question about how it affects the values of the voxels and how it affects the processing steps after that. So when resampling, I think the values of the voxels change, doesn't it?
Yes, they change, but they are computed from the original values.
Yeah.
So usually they are interpolated. So you compute a value that's between the two values that you need, or you skip a value if you want to reduce the resolution. It depends on how you do it. There are some methods that can cause artifacts actually, and well, you should be aware of that. So the easiest thing would be to just do like a linear interpolation, then everything's fine, but it doesn't look very realistic maybe. And there are other filters that are better under most circumstances, but they can cause problems. That you should see that. And actually, if you do it the same way and you adapt your segmentation algorithm to that, then it shouldn't be a problem. So it doesn't really change the information that's in the image, I would say. Okay, so yeah, I added some notes here. So in general, I can show this first. So by the way, the software is called MEVIS Lab, and it's not a coincidence that it's called MEVIS Lab, and I'm from Fraunhofer MEVIS. It's not actually from Fraunhofer MEVIS because there is also a company called MEVIS, but the company and the institute have the same kind of origin, and basically this MEVIS company was a kind of a startup from the research institute, but that was also like 20 years ago. And we are still using that. So what you're using now is what we are using every day, basically. It's the free version, so you don't have all the features, but that's what we're doing. And in MEVIS Lab, you always go from bottom to top. So you load images, or you have some way to get images. Then you do things with them, and then you have usually a module to view results. We call these modules, so these are different components that do different things. And now here you can just, if you open it, you will get the lung lesion, but there is also a liver lesion and an MS lesion. And if you click on the viewer, you can see them. And actually these images are really small. I did that because that's what an algorithm would see. So if I click in a lesion, for example, and then the algorithm would not work on the full image, but it would extract a small region. And here you should be able to draw contours. Yeah. I will walk around a bit and see.
Right on it, you can draw a contour and it will mark a region.
Yes. Yeah, exactly. So I shouldn't have stopped. You have to draw the contour completely like this. You can choose if you want to do the lung lesion or liver or MS. You don't have to do all. That's too much. So anyone having problems with this?
Çok kapandı artık zaten.
Yok yok. Ona zoom sallanıyor ya. Onu sordum. Ekranı kapandı yani. Onu sordum.
Also, we meant to do that. There is a note next to the thing next to the view to leave module. So I didn't do it right either. I should have changed the windowing here. To something like, yeah, this is what you would usually do for a lung CT. And maybe if you do that now, then you will realize that your contours don't look correct anymore if you change it. That's something that, especially for lung lesions, because you have a very broad area around the lesion where the values go down, and with different settings, it looks different. And then when you do it, you can think about these two questions. How hard do you find it? How confident are you that you're doing it correctly? And also, what do you look at in the image, basically? And also, what kind of prior knowledge do you use when you do that? I didn't tell you anything about lesions, but I think you can still do it, but you can use some kind of implicit knowledge, I guess. Not good, probably.
Can you ask something?
Yes, sure. Yeah.
You stack with the line option. There's
I'm not sure if it works if you don't have
My mouse. Okay, double. I
This
thought
is like,
it was
this is, I think this is the right mouse button.
Okay, Sinir bastı hiçbir şey yok. Bence çok olmuş. Benim evet. Çok oldu. Kaç oldu? Bütün yukarı aşağı yaptım.
Any more questions or problems? So I think maybe we can continue. You don't have to finish it. It's just about the experience. What did you observe, or what would you say to these questions? Did you find it easy or hard? And are you confident that you did it correctly, or do you think there may be different possible segmentations? Yes.
It can be very subjective. It depends on the person who will do the segmentation.
Oh. Yes, definitely. Oh.
I would say I find it hard because it's so blocky, so it's not a smooth image, and of course the border region is the problem, and that leading me to my which features and what prior knowledge I use. What I then do is I kind of average, so I take into account some pixels that are voxels that I would not count into, and while I leave out others, so I do that on a natural way. I start averaging over here.
So you're trying to get the correct volume that you want to have by adding a voxel here and leaving it out
so it's
there.
the
maybe.
best guess in the middle. Like that.
Yeah, that's actually, I think that's what most people would do. Anything else? You saw already that it really depends on this window setting. So I did this, I think this looks good. Now if I change the window, it doesn't look good anymore. So you need some kind of predefined window, or well, actually if you do it manually, you need a predefined window. That's of course the advantage of using an algorithm which doesn't care about the window, it just cares about the values. I have collected a few things that you could have observed. Maybe you mentioned most of them. So the first thing that I think everyone just assumed is that you have different intensities in the lesion than in the surrounding tissue. That's the kind of prior knowledge that you used. I didn't tell you that you should segment the thing that's brighter, but you just assumed that somehow. And it's correct, of course. Then you also saw maybe that the lesion has contact to these other structures that have the same intensity, namely these things here. They are not part of the lesion, they are blood vessels that pass through it or close to it. So here you shouldn't have included them. But that's of course something that you need to know, or that That's prior knowledge that maybe not everyone had. And that's something, of course, that you would also have to teach your algorithm. Don't just segment everything that's bright, but take care that there can be other structures that look similar. Yeah, we also talked about the shape already. So these lesions are compact. That's kind of part of the knowledge that the vessels are not part of them. Sometimes maybe you had to check the neighboring slice to get the right segmentation for your slice that we're currently looking at. So kind of use 3D information. And also, as Klaus already said, the boundaries are not sharp at all. So you need to define your boundary, your threshold basically, where you want to draw the boundary. Okay. Then I would like to talk a little bit about quality criteria for segmentation algorithms next. So probably the most important thing that you would think of is accuracy. So you want to have an accurate algorithm that works correctly. I will talk more about that in a minute, but there are many other quality criteria that are sometimes overlooked or not weighed as much as the accuracy. The one thing is reproducibility. That means, especially if you have a fully automatic algorithm, you get the same result regarding independently of who's using it, because, well, it's just fully automatic. But you could also want to have an algorithm that is not, if it has a user input, that it shouldn't depend on it too much. Like if I click into a lesion, I still want to get the same segmentation regardless where I click into the lesion, which is already something that's usually not the case. So that's something to consider. And then efficiency, again, you shouldn't slow down the overall workflow, so the computation time is important. If you have an interactive method, you click in it, you don't want to wait a minute. But also if it's fully automatic, you don't want to have your resources like computing for half an hour. Or maybe you have, that depends on your setup and your hardware that you have. Then what kind of hardware you need. For example, for deep learning based methods, you often want to have a GPU, which not everybody has, especially in hospitals. I think it's not, you cannot assume it. So what are the hardware requirements? I would also consider that part of efficiency, to be like resource efficient. And also the amount of user interaction. Do you just have to click? Do you have to basically draw almost, maybe do you have to draw a full slice manually and then the rest is done by the algorithm? Do you have to correct it often because it's just not good? Then that could also be a criterion that an algorithm maybe is not so good or will not be used. And then the fourth one is trustworthiness. That's just an overall term that I used here. So for example, plausibility is an aspect of this. If you get implausible results, sometimes you can lose trust in an algorithm. And then you will just not want to use it anymore. That's something that happens. Or understandability. Do you understand when it fails? Is this, or is it predictable that it will fail in certain cases? And that can also be important. If it just randomly fails, sometimes you will again lose trust, maybe you not want to use it. And then adherence to the user input. So if you click somewhere and it segments something else, that's also something that you wouldn't want to have. So it should use the input that you gave it in a reasonable way. Now there are some conflicts between these different goals, of course. So what do you think, or where do you think there is actually conflict?
Simply independence of user input and adherence to user input is like conflicting.
That's the most obvious one, of course. But do you have other ideas where you could have to make a trade-off, or you have to decide if you want to have that or that?
Accuracy, efficiency, because of the computation time.
Yes, yeah, that's also quite obvious. Other ideas? I think there are more.
More?
I think so. Well, for example, I mean, accuracy and trustworthiness can actually be a conflict. So I had an example where I had an algorithm that didn't always return a result. Sometimes it just said, I don't find anything here. And then you can actually increase the accuracy by putting a sphere there, somewhere in the middle, because it's still better than nothing. But it's not plausible, or not predictable. So that would be another example. And I think there are even more. So how can we measure accuracy? Most of the time what we do is we compare the results of our algorithm to manual segmentations from medical experts, which are often called readers. And that could be anything from trained and experienced radiologists, radiology technicians, or other people, to medical students who just do this as a student job. It's important to realize that if these expert segmentations are not fully manual, they can have a bias. So if you use another algorithm to create these segmentations or a specific tool, they are not, well, there's a bias. And in particular, you shouldn't use your own algorithm to create reference segmentations for testing, because then it will definitely look better than it actually is. Because as you just realized, there can be different segmentations that are correct, but if you choose the one that your algorithm produces, and then use that to evaluate the accuracy of your algorithm, you have a bias. And then the other thing that we also already said is that there is no ground truth. So there is not the one correct segmentation. And do you know why I put this image here? Any ideas? What does this have to do with what I just said? Ground truth? This is where the term ground truth comes from.
Really?
Yes. You take images like this, and then you go to the ground and measure. And then you have a truth. Then you have the correct measurement, and you cannot do that for medical images. And that's why you shouldn't use the word ground truth.
You always use it.
I know, everybody's using it.
That's not too much.
Best guess? What's the alternative? Best guess?
I would call it reference segmentation, because it's kind of the segmentation that you have. You can also call it expert segmentation, manual segmentation, whatever, but don't call it ground truth. Maybe that's at least one of the most important messages of this session. What you can also do as an alternative, and then you could also have a ground truth for a medical image, is a phantom. So either a software phantom where you take an image of a healthy patient, or at least a patient without lesions, for example, and you insert lesions into the image with a known size. You can do that. I don't know, maybe this is not very realistic, or it has other problems, let's say, but you can at least find out if the correct volume of that ball or whatever that you inserted into the image is computed by the algorithm. And another thing that you could use are physical phantoms, so it's really something like this. I have never seen something like that in real life, but you can actually build things that look like organs and have lesions in them, and then take images of them and segment them. You can do that.
I have to say, in MR, this is really tricky.
Yeah.
Because then you need to find some sort of material which is water-like, and that's, we tried it actually, and it's really, really tricky. So MR, it's a procedure.
And it's also obviously a lot of work, and it can cost a lot of money to get the right material and everything. It's not often done, as far as I know. So how can we now actually measure the similarity of of two segmentations, or one algorithmic segmentation and your reference segmentation. We are here now considering a binary case, so we just have one structure and the background. If we have multiple structures, we can just do it for each of them. And it's voxel classification. So we have, for each voxel, we have a label that can be correct or incorrect. And now we could do something like sensitivity and specificity, which we usually use for classification. But the problem is that you have a lot of true negatives. So it's easy to label the background correctly. And also, the size of the background depends on the size of the image. So if you want to segment a tiny lesion in a huge image, you will always have almost perfect specificity, I guess. So you shouldn't consider the background values when you evaluate a segmentation algorithm, because it's, yeah, as I said, it's easy to get it right and the size can be very different. What we usually do is the dice coefficient, and this is just an example. Have you all heard about the dice coefficient? Do you know how it's defined? Okay, then maybe I don't have to explain it too much. So it's just, yeah, you can see it here. So you have a formula and you have two segmentations. You compute the intersection and divide it by the sum of both, and then you get a number, which in this case, and this is also interesting, looks quite high, so it's almost close to 1. But in 2D, it's always easier to get a high dice coefficient than in 3D, because the slices where the object ends are always the hardest, and you don't have them. Then there's the Jaccard coefficient, which is also called volume overlap or intersection over union. Just remember, it's totally equivalent. You just need one of them, and the dice is always a little bit higher. So you should always, yeah, most people use the dice, I think, because of that reason. It just sounds a little bit better. You can see that only 0 and 1 are equal, and otherwise the dice is always a little bit higher. And it's just a matter of computation.
Maybe you come to that later, but when I do optimization, it can make a difference, right? Because I have different optimization, like different gradients on those positions.
I don't think it, yeah, but it's not a big difference. I mean, the gradient direction should be the same, just the gradient strength is different.
Yeah.
But yes, that's a theoretical, I've never thought about that actually.
Ah, okay.
But yes, it can make a small difference, but in theory it shouldn't make a big difference. There are two properties of both of them, obviously, that you should be aware of. One is that they are higher on larger structures. So if you have, for example, you have an organ, you would expect a dice of 0.95, I would say. If you have a lesion, you wouldn't expect that, and the reason is that the percentage of boundary voxels, because they are interesting. It's easy to segment the inner part of an organ or a lesion, but the more boundary voxels you have in relation to the size of your structure, the higher your dice and Jaccard coefficients will be, and that's also expected. That's one thing, and the other thing is you cannot distinguish one big error from many small ones, because you just look at the number of voxels that are correct or incorrect, not at their location and how many of them are close together. And therefore we also have another accuracy measure, which is surface distances, or in 2D this would be contour distance. And here we're really talking about contours now. And if you don't have contours, you can grade them from your voxel classification using different methods. But here let's just look at these two contours. So what you do is for each point, and of course if you sample the contour, you can really do it analytically. You compute the distance to the closest point on the other contour. And this is not not invertible. So you can, from here, the closest point would be this one, but from here, the closest point on the other contour would be that one. And you do this everywhere, and then you can either compute the mean of that, or, for example, the maximum. And that is, the maximum is then called Hausdorff distance.
Jan, in comparison to dice score, the Hausdorff distance I feel like is not as accurate because the maximum distance might be too much, but then overall the fitting might actually be nice. I mean, the segmentations might be actually close to each other, but there might be a glitch. What do you think?
Yeah, that's exactly, no, I didn't write it here. That's exactly what just popped up.
Yeah.
That's the problem of the Hausdorff distance, that it's very sensitive. So if you have a perfect segmentation, but one region that's incorrect, I mean, that's what the Hausdorff distance tells you. You should not only look at the Hausdorff distance, but you should always combine it with something like the dice. And
It might be nice actually to see, how much of a variation overall exists at most. So it might be nice to report both.
Yes.
Okay.
I would recommend that that you have one like overlap measure like dice or Jaccard and one probably the Hausdorff distance. Then some people also use for example, the 95% Hausdorff. So it's not the maximum, but the 95 percentile of this distribution of distances that you get from here. That's not as sensitive as the actual Hausdorff distance. And then these two are, or these surface distances are independent of the structure size. So that's good. If you do it for for a lung and for a lesion, it just tells you an absolute value, and it's just how far you are off from the correct segmentation.
I'm not sure about the structure size. So what you mean with independent of structure size? So if it is a small structure, then this distance might be smaller, right? The maximum distance actually.
Yeah, but that's then a property of your algorithm,
Right.
and not of this measurement.
Right. But then, what do you mean with independent of the structure size? That's what I was thinking.
I mean that you don't kind of automatically get a lower distance because your structure is larger.
Oh, I see.
So because it doesn't depend on the amount of boundary surface.
Oh, okay. So the size of the structure.
Yes.
Okay.
Of course, you can say that it's hard to segment. I don't know, maybe if you want to segment an organ, your algorithm will probably make larger errors because, I don't know, it has to change to downsample it or something like that. Then it's, of course, not independent of the size. But that's, in the end, it's a property of what you're doing and not what you're measuring
What you are
with
measuring.
the
I see,
distance.
thanks.
This is another example. This is actually from my PhD thesis, where I also had a chapter on there is no ground truth and there is a huge variation in manual segmentations, and you shouldn't call it ground truth. Look at this. These are 10 experts. They are,
Oh no.
some of them are radiologists, some are radiology technicians, but they are very experienced, probably more experienced than radiologists in manual segmentation. And these are 10 liver lesions, and sometimes they agree quite a lot. The second number is a measure of agreement, or of disagreement. So if that's low, it's good. And the first number is the volume of the lesion. So you can see also here, for example, that for larger lesions, of course, the variation is lower, but that's just because, again, that's the same effect as with the dice coefficient. It's just lower because in relation to the overall volume of that structure, the error is not large. But I think probably in terms of distance between the contours or surfaces, it's the same everywhere. And now imagine you use one of these randomly to evaluate your algorithm. It's what you often do because you don't have these 10 contours, but it's obviously better to have more information about what kinds of segmentations can be considered as correct by experts.
So then if you use some kind of loss function for deep learning models, like only the difference between the two contours, like then you will be having difference between the borders instead of having the inside region. So it will be more accurate to measure the important relevant points. Like, for example, in the first example, as you said, the inner region, the lesion is big, so because of that the inner region is big, and because of that there's any error on the edge is not affecting too much. So because of that the deviation is low. So if you do something like having the difference between the borders, like as for example from the second one, let's say, if you get the difference between the blue one and the red one, you will be having a kind of area. So you can measure that area and then say, okay, the difference between those regions from the edges is that, and then it kind of try to learn to overlay the edges on it. So then the score will be independent from the inside region.
Yeah, that's something that you can do. You talked about loss functions already. Actually, the typical loss function is the dice, but there are other loss functions that use something like the surface distance that I talked about. I think it's called boundary loss, and that would be one way to deal with this. What you could also do is you could weight the loss with the volume of lesion. So you could teach. I'm jumping a bit ahead now to answer the question. You could teach your algorithm to to give more weight to these cases that are more difficult, and then you get a similar effect at least, even if you use the dice loss. So I don't know why this boundary loss isn't used a lot, but as far as I know, it's not used a lot. But maybe that's also because it's most important for structures that can have very different sizes, like lesions. If you want to segment the liver, you don't need it, because then you always have more or less the same size. And here you can have really a huge range. I mean, look at these below 1 milliliter, and this is more than 50. But yeah, you're right. There are things that can be done about this. So what can you do now if you have these multiple reference segmentations, which is of course the best thing. And I'm still talking about evaluation now, not about training. We cannot usually expect to be closer to any expert segmentation than another expert segmentation would be. So if you kind of compute the dice coefficient between these here, that's kind of what the best thing that you can expect for your algorithm, because it cannot be more accurate than this, unless someone made an error here, and maybe you find that out. So you can use the similarity of these algorithms kind of to calibrate your expected accuracy of your algorithm. And you can do that, for example, by doing pairwise comparisons. So you compare all of them in pairs, and then your algorithm with each of the reference segmentations, and average that, and then you get at least a feeling how good you are. And what you can also do is you can create a consensus segmentation. So you, for example, you average or vote over your expert segmentations, and then that is your reference. But then at least it's kind of expert independent if you have enough experts. And it's of course impossible to say how many you need, because each of them will do it slightly differently and will add information to your reference segmentation.
May I ask a question?
Yeah.
For consensus reference segmentation, what would be the criteria? Let's say you have 10 experts. Would you maybe choose a cutoff of like 70% of the experts chose this voxel as a voxel of the segmentation and then admit it? Like, is there a criteria for that?
No, you have to. There's no established criterion, so you have
define
to.
it then.
I think I would say 50% if you assume that all your experts like have the same level of expertise. Otherwise, you can weight it with I don't know how long they have been working already, something like that. But that makes it really complicated.
Okay.
That's not something that's usually done. So what most people do, right, is just cut it at 50%. I would say.
Thanks.
Then some other things. It's and that's again something that's often forgotten. You should not just compare your algorithm to reference segmentations and report that. If you write a paper, for example, you should talk about necessity and effort of correction. So how often do users feel that they have to correct the segmentation to get the correct result? For example, if you want to measure a volume, it's not necessary to correct all errors, because often you will have just small errors at the boundary. Sometimes you will have too many voxels here and too few voxels there, and it will average out. Or you would have drawn it differently yourself, but it's okay. If a colleague could have done it like that, something like that, and then you wouldn't need to correct it. But it's important, I think, to report or to have a study that tells you how often users did correct the segmentation. So I think that's more important than a dice coefficient. Dice is for comparing different algorithms, but in the end, for practical application, you want to know, did the users accept it, and did they have to correct it? Also, were they satisfied, and did they trust it? How did the users feel about using the algorithm? That's what you want to know. And that's not something that the dice coefficient can really tell you. But of course, that's hard to measure. It takes a lot of effort. You need these readers that do a study with you, and also then you cannot really compare algorithms like that, because then you have to take into account, for example, how are the results presented, what kind of correction tools do you have, and that's really hard to standardize. One approach to standardize comparison of algorithms is our challenges. So challenge is kind of a competition where you get a task. You often also get some data, and then you are supposed to submit an algorithm, which will then be evaluated on a test data set that has not been published before. And then if you organize such a challenge, you define some quality criteria, and then you get a score. You compute a score that combines, for example, dice and Hausdorff distance, and maybe the computation time. In the end, it's also subjective, but at least you have the same criteria for all participants here. And these challenges are often connected to conferences. You often get a paper in the end. So if you're interested in the state of the art for a particular segmentation task, it's a good idea to check if there was a challenge recently. That's something that we also do. So we have, for example, last year we participated in a lesion segmentation challenge on CT, so exactly what I was talking about. And we will hopefully organize a challenge ourselves this year. So this is just something that you do. It's not something that only like special people do. Everyone can basically do it. And most of these challenges are hosted on a platform called Grand Challenge. And you can also look up the website. So this is organized by the Radboud UMC. It's a university hospital in the Netherlands who has done a lot for challenges. And this is just a screenshot from that website. So you have many different things. These are all challenges, I think, that took place last year or will take place this year. It's really a lot. It's like 30, 40 challenges per year.
Are those online?
Yes. So usually you have to register to participate and also to get access to the data, but they don't really check you. They just want to know, I think, how many people have that data.
it a little interactive here. Have anybody of you ever attended a challenge? No? So I think if you are like, in the end of any project you are doing, and if you are having not only your task for segmentation, but any image or data processing, there are often challenges, and I think if you, in particular if you are a team, it's really motivating to take on such a challenge. It really, it helps you to focus for a short period of time, and I think in particular when you then see others' results, it's also opening your mind for new solutions if you are stuck in whatever problem you are currently facing during masters or PhD students actually. So it's, I only did it once, but it was really like, you normally have a steep learning curve because you have, you just have this, as you deadlines, you just have some pressure, but I mean, you basically don't risk anything, but it's, it helps you focusing, in my opinion.
Yeah.
In these challenges, are they like publish some kind of abstract for the approach, or do they share their code?
There's both. So usually you have to write a description of your algorithm, but now the trend is that you should actually publish not the code, but a Docker container containing your algorithm, so that others can reproduce it. Publishing code is usually not required. Okay, I just realized that this was about half of what I prepared, and I think it's we have like 25 minutes. We started a bit late.
We started late, so we have time.
Yeah. So if there's anything now that all of you know, just tell me. Then we can skip it because that's possible. I don't know. But I will just continue for now. Maybe it will take a little bit longer.
Yeah, I mean, whatever works for you. So.
Yeah, no, for me it's fine. Okay, so as I said in the beginning, I've been working on this topic of lesion segmentation since basically 2006. And now I want to compare what we did back then and what we're doing today. What we did back then is we looked at some cases, and by some I mean maybe we had 50 lesions, and on, I don't know, 30 CT scans. We looked at them, we talked to radiologists, or we just made our assumptions what the expected segmentation is. I'm not talking about segmentations with manual segmentations, just the images. And then we experimented with basic building blocks until most of the cases worked. And then typically someone found a new case where it didn't work because we hadn't thought about something. We adapt the algorithm, or maybe we realize, oh, we need a special handling for something that I don't know, there's a type of lesion that we haven't seen before, we have to adapt it. And then typically these last two steps were just repeated. A new case came up, or maybe there was a challenge at some point. We actually had a challenge, a liver lesion segmentation challenge in 2008, which was one of the first challenges ever at that time. And we just realized, oh, we lost because one of the cases didn't work. I think they had like 13 lesions in the test set, and one of them we completely failed, and that's, in the end, I think we at least we didn't win. And then of course we wanted to adapt the algorithm, so that's what happened. And what we did for this algorithm at that time is we decided we don't want to do fully automatic lesion segmentation. But at that time we said, okay, we want to add information. We want to create a segmentation and calculate the volume. And what they did at the time was drawing a diameter, so the diameter measurements. And we thought, let's just use that diameter as the input to our algorithm. So we know where the lesion is and also how big is it approximately. And we were able to cut out a region of interest from the image, and didn't need to process the whole image. And we also decided, and that will be important, to resample it to an isotropic voxel size. And then the easiest thing that you can do, and that's actually something that works relatively well for lung lesions, is to use thresholding. So to define a value or a range of intensities that you just add to the lesion. And as you saw before when you did the manual segmentation, yes, you get the lesion. And actually, this is a fixed threshold. So for lung lesions, as I said, CT is calibrated. We use the fixed threshold value here, and then we get the lesion plus this vessel. Of course, you don't always have such a vessel here, so many cases already worked well like that. You can also see here the 3D rendering where you see there are actually separate vessels that are connected to this one. How to remove them is one way is to use morphological operators. Who of you has heard of that? I don't know, people still... interesting. That was really, I mean, when I studied computer science, or we had some image processing courses, this is one of the really basic things that we learned. And I always had the feeling that nowadays it's really not used anymore.
I think it's used for especially getting rid of, I remember using it many years ago for removing the skull and then removing the voxels that are kind of not there, like the ones that are not removed properly, using erosion.
Yeah.
And for dilation, I remember using it for estimating some parameter more accurately, so I needed a little bit outside of the brain. So all of them are quite useful algorithms.
Yeah, well, you said many years ago, and that's what I would say as well.
Yeah, many years ago,
So,
of course.
Yes.
Yeah.
So this was really one of the building blocks, as I called it before, that we use all the time. Thresholding, morphological operators, and some other things that will come up. So if you haven't heard this before, erosion means basically you can look at this example. You have a segmentation like this. You just erode it at the boundary. You make it smaller. Basically, I will not go into the mathematical definition of this. And dilation means you just dilate it, basically, as the name said. The interesting thing is if you combine these two. So if you first do a dilation and then an erosion, you get from this here, because if you dilate it, you add these ones, but also the one in the middle. And then if you erode it again, this hole in the middle will not come up anymore. So that's why it's called closing. And opening is the same vice versa. You first do an erosion. So erosion in this example here means that all these voxels will be removed. And then you just have this inner part, and then you dilate it, or actually you just have one voxel left. And if you dilate it again, you get this. You can try that out. That's part of the next hands-on session. And so the idea that we had here, we had these vessels, was to first apply so many erosions until these vessels are not connected to the image boundary anymore. So remember, it's not the full image, it's just a region of interest that's adapted to the size of the lesion. So we can do it like that. So this is the first erosion. You can also see that the vessels get thinner and also shorter at the end. And then at some point the vessels are gone, and then you can dilate it again and get basically the correct segmentation that you want to have. In practice, you don't do multiple erosions. You can, this erosion has a parameter called the kernel size, which tells you basically how much you want to erode and dilate. But you can try that out now. That's the second MLab file that you should have. And here basically if you can just see how I implemented this, what I just told you in MEVIS lab. So if you open this, you get a good looking segmentation, but you can take a little time to change the threshold here, and also to change the kernel size of these two morphological operations. Are you recording again? Yes, okay, please. Then let's just continue. How about liver lesions? So we talked about lung lesions. Lung lesions, as you probably saw, have a strong contrast. So they are completely different intensities than the normal lung tissue. But for liver lesions, this is actually quite a typical example. So you can see it, but you can also see that there is quite an overlap in the intensities between lesion and healthy tissue. And so if you would just apply a threshold, you would get something like this. So you have some holes in the lesion, and you have some other voxels outside that are also segmented. So what can we do about that? We could use morphological operators maybe again, but this time we will do something else, because you probably, if you look at this liver lesion, you could probably easily segment it. You wouldn't be like disturbed by these overlapping intensities, I guess. And that's because what your brain or your vision actually does is to smooth out this image, and you would see, or what your, I don't know if that's true, and I shouldn't maybe say that in a neuro imaging workshop, but I think what your brain actually sees is what you can see on the right. And then it's, again, there is a threshold where you can separate the lesion from the healthy tissue. And what's achieving this is called the average filter. And what this filter does is it just replaces the value at a certain position by the average of all the neighbors. And now, probably you cannot see it, but I wrote some, well, it's really impossible to see it here. You add up these values here and divide them by 9, because it's 9 overall. And then you replace this value by this, and this is what this average filter does. And now you can do this a little bit differently. You instead of adding them and dividing by the number, you can also, and again you probably cannot see it, you can also multiply each of these values by 1/9 and add them up. That should be the same, right? And the reason why I'm doing it like this is because this is an example of a general concept called convolution. And convolution means you take a region, so all the neighbors of a particular voxel, multiply them with a value that comes from something like this, some kind of matrix, and you add them up. So convolution means multiply with some value and add up in a neighborhood. And then the result goes into the middle of this neighborhood. So, and of course these three are all the same. 1/9, it's approximately 0.11, and you can also write it like this. This is what you will see most often. This is convolution. This matrix is the kernel. And this is really important because it's the basis of what you're doing in deep learning, which I will come to in a few minutes. And then you can do other kernels to average. So for example, this is a 3x3 neighborhood. Of course, this is now an example in 2D. In 3D, it would be a 3x3x3 kernel, and you would also include the neighboring slices. But in 2D, it looks like this, and then you can have a larger neighborhood. So you can, and you saw that before, we had this 3x3 and 5x5. Of course, the effect of the 5x5 filter is just stronger because it's averaging over a larger region. And you can also have something like a Gaussian kernel where you have weights that are not the same, so it's not an average, it's a kind of a weighted average, and the voxel that you're actually looking at and its direct neighbors has a higher weight than those that are further away. Any questions about this? Because this is important. Or did you know that already? Did you know that already? I think most of you did. This should be, okay, this is probably basic knowledge because it's still relevant for convolutional neural networks. Now, what would this convolution do? Any ideas? So if you compare this kernel, something like you you just have ones and then some factors, and here you have something different. You also have negative values. Yes?
Is it the derivative on this lattice?
Yes, exactly. So it's, if you have an image like this, the result would be this, where you probably cannot see much. But let's do it like this. So if we first apply an average filter, then you can see if you look from the top to the bottom, if your image value goes up, this value here is low, and if your image value goes, here it first coming from up here, this is a higher value, it goes down, so the difference is negative from one voxel to the next, and that's why we have negative values here. You can see the boundary of your lesion here, and you can see that it's a negative boundary in the sense that the values go down, and then here they go up again. And we can do the same thing in the x direction. Then the kernel looks like this. And did everyone understand what happened here? So what this kernel did? Well, basically you subtract the value, well, the right neighbor from the left neighbor, or the bottom neighbor from the top neighbor, and that gives you information on how the images change along that dimension. And therefore here it's really hard to see, but you get something similar. And then the interesting thing is if you combine these two, so you take this and this, so squared, add them, and apply the square root, then you get something that's mathematically the gradient magnitude that maybe some of you have heard about if you're interested in mathematics. And that's kind of an edge detector. So now you really just get a high value for those voxels that are on the boundary of the structure, where there is change in any dimension, you could say. So that's convolution. It's the same thing that we use for smoothing with the average filter, the same mathematical thing that's happening here. And I just wanted to show you that you can do very different things with convolutions, and it's just an abstract concept basically, but it's very important. Now, we were segmenting liver lesions, and I said let's apply this average filter, and now we still need to find thresholds for segmentation, because in the liver you can have different contrast agent phases, and you can have different types of lesions which look different. So compared to lung lesions, you cannot just use a fixed threshold. You need to adapt it to what you see in your actual image. And what we did here is we used this input diameter that was drawn. I said we have this diameter, so we dilate that a little bit. This would have been the input diameter that was drawn by the user. We dilate it to get more voxels to do some statistics, and then we compute two histograms here. So one is of this complete region of interest, where you can see mostly the healthy liver tissue represented in this histogram, but you can also see the lesion down here. But that's not always the case. So we just used this histogram to find the typical liver tissue value. And then we used another histogram, just this area of this dilated diameter, and we get another typical value for the lesion. And then we just used the average of these two values as the threshold. If we do that, we get a nice segmentation. So that's what we did for liver lesions. Now, there would now be another session to try it out, but I would say you can do that at home maybe, or in the evening. You have the network and you can just try it out. I don't think we need to do that now. So that was the basic ideas of what we did. So these were algorithms for lung and liver lesions that we developed. Actually, we developed them for quite a big company at that time, and we licensed them to that company, and they were part of a medical product at some point. You know, maybe you're asking, was that really all? Is it really that easy? No, it's not. It was the basic idea, and it worked for many cases, but here are some examples where it didn't work, or that required special handling that we also added that I'm not showing you today. So for example, probably, I don't know if you can see the contour here, the white contour here, but this is a lung lesion that's attached to the lung boundary. And that's another problem that cannot be solved with morphological operations, because these, for example, this, I think this is some vessel, could be the aorta. It has the same intensities as the lesion, and now this one cannot be removed with opening and closing, because it's actually larger than the lesion itself. So here we had to do something else. We didn't have a lung segmentation at that time, so we really just had this small region from the image, because we, as I said, computation time was an issue. It was a time when even lung segmentation was not a solved problem, so we just didn't have it. So we tried to do something like a local lung boundary approximation here, which worked pretty well. Here we have the same for the liver. Also, liver lesions can, when they are at the liver boundary, they can look very similar to this muscular structure that we have here. Yeah, this could have worked with opening and closing, probably, but we implemented some kind of local organ boundary estimation here in addition. And then you can see in the liver we can have lesions that are actually heterogeneous. So where this approach, we have one typical value for the lesion and one typical value for the healthy liver tissue didn't work. Here we have actually two typical lesion values. Here also, and here the problem is that this typical liver lesion value was not correct, because we have so many other stuff that's not liver tissue. So we had to do special things here, which I'm not going to explain. Yes?
Jan, would it be possible to maybe define two regions of interest in that particular example, one liver only, and then one lesion, and then you would still apply your algorithm?
Yeah, that's something like that is what we did.
Yeah, okay.
So for example, we allowed to have more than one typical value for both the lesion and also for the. So we analyzed the histograms, looked if there are several peaks in the histograms, and we knew it was a certain type of lesion, and then we did different things that make sense.
That's fine.
But that's really then this kind of cases, you just see the case and you immediately know, okay, it cannot work here because some assumption is violated, and then you just add something to the algorithm until it works. So that's really what we did. And down here you can see some other examples that we didn't manage at the time. So here we didn't get any result at all, and the others are just bad for different reasons. I'm just saying it wasn't perfect back then, definitely not. But we were quite proud of it because, well, it was with what we had at the time, it was quite good, I would say. Okay, so how do we do it today? Today, the first thing I would do is check whether there is a public solution available. So for many things, especially organ segmentation, there are just publicly available trained neural networks that you can use. So many things are maybe already solved, and you should check that first. If you don't find something, then you really need to collect a large amount of data. So 50 lesions would not be enough anymore. You need a few hundreds or even thousands to be really good. But then you will be really good. And then you can still use the standard deep learning approach. You don't need to think too much about what you should do. There are solutions that you can just apply to your training data. So, totally different approach. That's what I want to say. You need more data, but you need to think less, I would say. So what is deep learning? And now this is really the fastest introduction to deep learning that I could come up with, because I don't think it's really important to understand exactly what's going on. What you should understand is, first of all, it's a kind of machine learning. Machine learning is a more general concept than deep learning, and it's using deep neural networks. Machine learning means you have some kind of model that you fit to your data. And the easiest kind of machine learning is something like this. So you have like this, like fitting a line to 2 points. So the model in this case would be a line, which is described by a formula like this. Y is a times x plus b, and a and b are the 2 parameters of the model that are adapted to the data. By optimizing some kind of loss, and by loss I mean the kind of the closeness of what your model will give you compared to the true values. And you will probably agree that this line here is quite a good fit, or the best fit to all these points that you can see there. It's not about how we optimize this, but this is really probably the simplest kind of machine learning that you can imagine. Theoretically, it's not machine learning, but it's not important right now. You have a model that has parameters, and the values for these parameters are adapted to your data. And now deep learning is just basically the same, but instead of 2 parameters, you have a few millions. So you can do a lot more things with your model and can adapt it much better to your data, and you can describe much more complex relationships between input and output. But basically it's the same, just times a few million. And in that sense, a trained neural network is the statistical model of the input data. So it somehow describes things that have occurred in the input data. It's nothing more than that. In general, these deep neural networks can be used for all kinds of data, and then there are different subtypes, let's say, for different kinds of data. So you can have images, you can have text, for example, you can have 1D measurements over time. And if you do it for images, you use something, and almost exclusively you use something called convolutional neural networks. So that's the kind of network that you use if you have image data. And of course now you recognize this word convolutional from before. So the thing is that we saw that convolutions can do many different things depending on this kernel, this little matrix that parameterizes them. And the parameters of this convolutional neural networks, in the sense of a model, are all the values in this kernel. So you can learn basically you can apply convolutions with some values. You can put anything in there and something will come out of it. It's really that abstract, because most of these convolutions will then not really have a clear predefined meaning. You will not have exactly an average filter or this derivative filter. But you will have something that the model will use to produce the output that you want. And now what you do is you have many convolutions in parallel. So you learn, you tell, or you build up your network to say, for example, I want to apply 32 convolutions on the input image, something like that. So that's indicated here. So you have these many different convolutions that learn different things, and maybe some of them will smooth the image, and some of them will compute derivatives, and they will do totally different things that in some way help. And then you do something called pooling, where you reduce the size of the image, and actually you reduce you increase the voxel size, because the convolutions, they always looked at the neighbors. And if you want to look at neighbors that are further away, it's more efficient to reduce the image size and then apply the same kernels than to use larger kernels. So that's basically just a matter of computational efficiency that you're doing that. And then finally, at some point, you have even larger convolutions to compute results. This was now really, I think if you have ever heard anything about CNNs before, you will say this is not a complete description and many things are missing, but this is just the main idea. Convolutions are parameterized during training, what they do, and then you have these pooling layers in between to be able to apply the convolutions like on different scales, that's what we say, so with a different neighborhood size. The reason why you don't really need to, in my opinion, don't need to understand exactly what this is doing is there are solutions that you can just use. And one of them, and probably the most important one, is the so-called nnUNet, which is publicly available. You download it, you give it your training data, and it will do everything else by itself. So it will, you don't have to care. This was from 2018, and they had a paper last year where they showed that in spite of all the other things that have been done in the meantime by other groups, it's still at least as good as anything. So if you have heard about transformers, for example, they're not better than this.
Really? This still holds, essentially,
Yeah.
although it's an algorithm.
Yeah, it's yeah. They evaluated this last year. They compared it for several tasks with several other architectures, so other approaches, and they were always at least as good as everything else. So really, if you have data and you want to train a segmentation algorithm, just use this. You don't have to. That's what we do as well. As long as it works, the first thing to try is this. And also, if you always have to compare yourself to this. If you write a paper on segmentation today, you basically have to do this anyway, because this is the state of the art. This figure shows a little bit what's going on. So basically, there is this kind of statistical evaluation of your training data. So some parameters are derived from your data, so are adapted to the data. That's what's called data fingerprint here. There are some other parameters that are fixed, so they just made some decisions that worked well, or that where you can argue that they make sense in almost all cases. There are also some parts where they adapt to what kind of hardware you have, and they tend to, we have to say that the nnUNet tends to be rather a little bit slower than you could be, but then it works on most hardware, something like that. So they go kind of a safe way in many aspects, which means it works, but if you want to be really fast, for example, there are things that you should change probably. And here are some examples from their website, what kind of data can be processed with this. So everything from CT, MRI, also microscopy images. You can do organs, you can do lesions, you can do whatever this is. It's probably some kind of cells or even smaller structures. This all worked by just giving the nnUNet the data and training it. And then there's even more by now, because probably it was actually, I think, to be expected when there is a framework where you can just train and it's good. Then someone would just go ahead and contour many images with many structures and train a huge model for organ segmentation on it. And that's what happened in like 2 or 3 years ago. The TotalSegmentator was released, And that's what you should also check first. So if you need a segmentation of the atrial appendage, for example, you don't need to train it. You should first check how well it works here. And you can just download it and apply it. It's free. It's just an nnUNet trained on a lot of cases. It also, they have also released it for MR recently with not as many structures, but there are also other groups who are working on MR models. This is really also the first thing I would say that you should look at. And then if your structure isn't there, train in nnUNet. Sometimes these have problems with pathologies, I noticed. So for example, if you have a liver with a lesion at the liver boundary, because this has been trained mostly on, not on healthy people obviously, but not on people with liver tumors. It's just most of them had a healthy liver. So sometimes the TotalSegmentator has problems with when there are lesions in an organ, especially at the boundary. They will sometimes be left out. So if you're really interested in segmentation of livers with tumors, then this is not sufficient, I would say. But then you can still use this as a basis to train your own model. So you could use, for example, this to segment many cases with tumors that you then use for your own training. It's also something that you can do. The one thing that you still need to care about is data. And that's because, as I said, these CNNs have millions of parameters, and they can memorize the training data, or they can overfit. So that means they basically, they have the kind of the capacity to just memorize the training data, and then they will work perfectly on the training data, and that's what they are trained to do. So you somehow need to make sure that they don't adapt too much to the training data, that they are still generalizing. And to do that, it's very important to separate training and test data. So you have a training set, and then you really need an independent data set where you test your algorithm on. And you should do that if you use lesion segmentation, you should do it on patient level. So you shouldn't use one lesion from a patient in the training set and another one in the test set, because they can still be somehow similar and it could be a biased evaluation. So test data really should be used once in the end, after your training and also after you have a good feeling with your, for example, nnUNet training, and you don't want to do anything else, really in the end. And ideally also really different test data from different hospitals, different scanners and whatever, to make sure that your model generalizes. And then we use a third data set, usually called validation data set, and that's needed during training, because you can have, sometimes you do multiple trainings, sometimes or often you look at the intermediate results during a training, because the training can take very long and you want to make sure that it's going in the right direction. So you will already evaluate intermediate models that you have trained. And then you often look at plots like this here. This is from the nnUNet. It's automatically created when you train. And here you can see the training loss curve that's going down. That means that the model learns to correctly segment your training data, which, well, this curve always goes down, or it should actually get a little more flat in the end than it did here. But then you also have your validation loss curve, which is this one, and this should not be too far away from the training curve, because otherwise that means that, well, it doesn't work well on cases that it has not seen before. So that's important. And if you read papers about segmentation, always check that they have an independent test set and not, that's probably the most common error that you can make, that you report results on cases that are too similar to your training data. And that's just what we did. So we used the nnUNet at some point. We had the we had a data set with more than 10,000 lesions, also different organs, and we just put them into the nnUNet. Some interesting observations that I made is, first of all, while we had these separate algorithms originally for lung and liver, and we also had lymph nodes and other things, we're now doing that with just one model that has been trained on all lesion locations, because it works, and because the neural network can handle that, which has the advantage that users don't have to choose where the lesion is, or they don't have to click on some menu and say this is now lung or liver, which is a big advantage. It is much more robust than what we did before. So even considering all the special handlings that we implemented at the time, this is just much better. It's really, yeah, that's how it is. The results do depend on the click point. So we use a click point and then we cut out. Now we are not using the diameter input anymore, but just one click, because we didn't know how to pass the diameter to the network. And the results depend a little bit on that, because the click point is the center of the image that's passed to the CNN. So that's something to take into consideration, because some people were surprised by this, because you think, oh, this neural network has learned so many things, why does it still give me a slightly different result when I move the input image? But that's something that's happening actually. That's we haven't really solved that. So it's right now that's one of the trade-offs. We say it's okay, it's so accurate and it's also so efficient. In this case, we don't need the reproducibility in terms of these quality criteria that I mentioned before. Another thing that was interesting is that the CNN always segments something at the click point. So you click, even if you click outside the body, this model has learned, because it was like that in the training data, that in the middle there is always something to segment. You can, of course, change that by also training it on images without a lesion, for example. But if you don't think about that, things like that can happen. And then we call that shortcut learning. So the model learns something that's not what it's actually supposed to learn, how a lesion looks and where it is, but it just learns, oh, in the middle, I should always segment something. And then obviously there are problems with lesions that have never already appeared during training. We observed especially like elongated lesions, like for example some MS lesions. Then we still get something that's round. But that's something that you can change with the appropriate training data. And another thing that I found interesting is that the computation time is actually comparable to the old version of the algorithm. So it's not the case that these CNNs are really fast. You cannot say that, especially if you don't have a GPU. You still need to think about, oh, what should I do to have a certain computation time. Okay, these are just some results. So it's a comparison of the old results, really difficult cases that didn't work before and that are now they just work. Although it's, I mean, look at this one. It's really, I wouldn't be able to construct an algorithm that does this, but the CNN has just learned it. Or also this is really, I don't even know where this is. Yeah, so it's just much better. And now this is the final thing I wanted to mention, my personal feelings, like with this transition from these classical image processing to deep learning. So I would say personally, it was more fun earlier because you had to. It was like solving a puzzle. You had the problem and you came up with a solution yourself, and it felt like I achieved something. And at the same time, I realized it wasn't good enough really for clinical use, what we were able to do at the time. And that was frustrating. It was not making me happy to have a PhD and know that my algorithm is not used, although it's in a product, because it's not good enough. And now today, well, obviously the results are much better, so there will be no way back to the old stuff. But then again, the failures can be hard to understand. So if it's still failing, you don't really know what to do. There are cases where I can't explain to anyone why this lesion is not segmented or is segmented badly. Sometimes I can, but sometimes I don't understand it myself. Then, therefore, I can also not do something about it, or I don't know what to do. It's still a lot of work, especially the data curation. So you have to, first of all, have the data and collect it, which is often work, and it's even more work, of course, for the clinical partners in the project who have to really collect the data and do the segmentations. So the work has kind of moved over to the clinical side, but also the curation, so selecting which cases I want to include in training and splitting training, validation, and test sets. It's still a lot of work, more than you would think. There are also often technical problems. So because you use computing clusters, you don't just use, like you just did MEVIS lab, and you have some modules and then you see the result. These trainings take long time. Sometimes they fail, or they just stop and you don't know why, because you're using hardware that is not under your control directly, or because you're using third-party code, because, for example, nnUNet, if it does something strange, you don't really know why or what to do with it. On the other hand, it's great to have so much public code that you can use. So yeah, obviously. I think it's much harder to write publications and to also do a PhD nowadays. That's what I think, because everybody's using the same methods, and how can you be different, or how can you be better than others? It's hard, I think. And what most people do is they change something in the CNN architectures, and then they find a few cases where it works better. But as these nnUNet guys have shown, if you really look at it for many applications, then it's often not better. So yeah, I don't know. And for me personally, I'm more focusing on clinical applications nowadays than on methods. So I'm interested in where do radiologists really spend time, what are they annoyed with, and how can we help there in terms of workflow, and what kind of additional information do they need. And then that's the most interesting part, I think, and then you just know what to do to solve the problem from a methodological side, I would say. Okay, that was it. I don't know what time is it now, but I hope it was interesting, and thank you very much.
Thank you, Jan, for this detailed segmentation talk. We learned a lot. I think,